Okay, this is the first of a few videos that are going to help you with reviewing for Exam 3. And Exam 3 is going to begin with the content that starts at the point where we took Exam 2. And that the first part of that content involved the electric field associated with two planes of charge. I'm going to start just by drawing a single plane of charge, just to remind you. If you have a single plane of charge, let's call it a positive charge. And remember, we define the charge density to be the charge that is on the plate per unit area. Actually, I should call this a charge density up here. And no plates are actually infinite, so there's going to be a finite amount of charge, the Q, and whatever the plate area is, A, we plug in there in square meters. And the ratio of the two would give us the charge density in coulombs per square meter. And the electric field associated with this positive plane of charge is always going to be directed away from the plane of charge on both sides of it. There's no reason why it would favor one over the other side. So both sides of this plane of charge are going to experience an electric field that's directed away from the plane of charge. And the strength of the electric field on either side of the charge is going to be the charge density divided by 2 times epsilon 0, where epsilon 0 is the permittivity of free space, which is the 8.85 times 10 to the minus 12. It's coulomb per Newton meter squared. All right, and then we talked about, okay, this is review, of course, this is all review, but let's say we have a charge with a positive charge density near a plate with a charge of negative charge density. And we have 3 regions associated with these plates. We have region X, we have region Y between the two, and we have region Z to the right of the two. Now, one of the things we talked about is the fact that between the plates, you're going to have the electric field created by the positive plate that's directed to the right, but we also have the electric field of the negative plate that is going to be also directed to the right. So I'll draw that in black. The result being that between the two plates, the effect is reinforced by the other plate. So you're going to have twice the electric field here that we did over here. So the electric field between the two plates, in this case, the strength of it, is going to be equal to the charge density on either one plate or the other, divided by epsilon 0. So it's twice the value that it was just for a single plate. However, the electric field at X and the electric field at Y are going to be equal in strength. Not anywhere on this side of the plate of both plates and anywhere on that side of both plates. Not Y, I'm sorry, that should be Z. And it should be equal to 0 because they're going to cancel each other out outside of the two plates. But inside the two plates, it has this value, and it is uniform, meaning that everywhere between the two plates, it's going to have the same value. All right, so we spent a lot of time talking about that, getting ready to talk about capacitors. There's something else I also wanted to talk to you about, and that is something we haven't spent a whole lot of time on. We spent a little bit earlier in the semester, but I want to revisit it and take it to a slightly different place, but a very important place. And that is, if you have a positive charge near a conductor, what is going to happen on the conductor to the charges that are free to flow around the conductor? And we talked about this earlier in the semester. We talked about the fact that this side of the conductor is going to have the negative charges gathering because they're going to want to be closer to the positive charge, whereas the other side of the conductor, you have positive charges, so you get this separation of charge on the conductor as a result of this charge being near it. And of course, we talked about the fact that if you touch this side of the conductor with your finger, which is leading to ground, you could drain off these positive charges. But I'm not doing that right now. I don't want to talk about that. I don't want to go there. I just want to have it be like this, so you get this charge separation. Now the question is, let me just make this a bunch of charges here. What if I have these charges there that are creating this electric field that looks like this? My question is, what happens inside the conductor? Does that electric field actually exist inside the conductor? And what I want to demonstrate to you is that it does not. Inside a conductor, if you have an electric field like this, that within the conductor, these charges that separated, these ones on the right and these ones on the left, are going to create their own electric field. And the electric field that they create is going to exactly cancel out the electric field that's created by the external electric field caused by this charge here, with the result being that inside the conductor, there will be no electric field, because the motion of these charges, the separation of these charges, generate their own electric field that by definition is going to cancel the one that's out external to the conductor. And the reason, it's kind of an interesting conceptual reason, if they didn't cancel it out, then there'd still be an electric field here that would cause more charges to move from one side to the other, resulting in them eventually canceling out. So we can comfortably say that inside the conductor, the electric field is going to be equal to 0. So that's an important result. And part of why it's so important is that this is true even for a hollow conductor. So imagine a conductor that's hollow, that has positive charges over here. You're still going to have this separation of charge occurring in the conductor, where the negatives go to one side and the positives go to the other, meaning that inside the conductor, the electric field generated by the separation of the charges is going to perfectly cancel out the electric field that's created by the external charges. So inside, you're still going to have 0. I'll draw it again to emphasize what that would look like. It would look something like this, where you actually are going to have, let me make these red pluses. You're actually going to have something that looks like this. So it's like the conductor kind of is it's almost invisible to the electric field. The electric field will exist on this side of the conductor, and it'll exist on that side of the conductor, but the conductor will just be sitting here, and inside of it, the electric field is 0. Why is this important? Well, imagine this. Imagine that here's your conductor. Imagine it gets struck by lightning. What's going to happen? Well, if it did, what happens is the lightning is basically a lot of charges that are trying to go somewhere, and they end up on the conductor. Of course, it can be really dangerous. You don't want to get struck by lightning. But if you were inside this conductor, you'd actually be safe. So this is really, even if you're touching the side of the wall of the conductor, because all of the charges, even quite a bit, let's say a number of coulombs, they're going to all be sitting outside the conductor. They're on the outside part of the conductor. Now, you wouldn't want to be on the outside of the conductor with your feet on the ground, touching it in this case. That would be a no-no. But if you're inside the conductor, you're safe. So this has really practical implications in the sense that if you are in a car and in a lightning storm, the lightning can actually strike the car and you'd be safe. You wouldn't get electrocuted or anything like that. And I have a picture of it. I had it posted on my office door for a while back in the days when I could go into my office. And it's a picture of me being in something called the cage of death, which is basically a metal cage that you go inside and shut the door, and it's a demonstration up in Washington State. They have this little electrical museum, which I insisted on going with my whole family when we're visiting my daughter there. And what happens is they put this enormous electrical shock on, or electrical field on the outside of the conductor. There's sparks and all that stuff. Meanwhile, there's a bunch of people like me sitting inside this cage, and we're touching the wall of the cage, and you can see sparks all around us. Yet, we are safe. So there would be me, and there would be these sparks flying on this thing. Looks kind of like this. It looks really scary, but we're in there. We hear it. We hear everything. We're touching the inside wall of this cage, but we're absolutely fine. Okay, so that is a phenomenon about conductors, that the electric field does not exist inside of them. And I think that is enough of a material for the first review video, and there'll be at least one more.